Okay, so for the second part of Lab 9, we're going to be looking at a data set on the birth weight of lambs. And so this is from a study done here at Massey of mixed age Border Leicester crossed Romney ewes, which were randomly allocated after pregnancy diagnosis to a experiment involving 2 shearing treatments. So they were either shorn on day 70 of pregnancy or they weren't shorn. And so the study was primarily focused on whether the shearing made a difference. In addition, obviously we knew their pregnancy rank, so were they having a single lamb or twins, and they were then allocated to 4 feeding treatments, HH, HM, MH and MM, where the M stands for maintenance. So they were fed at a level calculated to maintain a standard weight, while the high feeding groups were fed to gain around 100 grams per day above the normal maternal maintenance weight during the relative period. So they either were on essentially additional food for the entire period, additional food for the first half up to day 101, and then maintenance for the last half, or maintenance for the first half, high feeding regime for the second half, or maintenance all the way through. So those are the 4 feeding treatments. And then we have whether they were shorn or not, whether they were having a single or a twin lamb or not as well. Okay, so of particular interest is how the feed management and shearing during pregnancy influences the lamb birth weight. Okay, so we're going to read the data in and do some plots. Okay, so we've got a difference in the birth weight of lambs depending on whether it was a male lamb or a female lamb. So the male lambs were heavier. Quite a bit of overlap though, but there seems to be a shift. The distribution is about the same. Obviously a difference in terms of whether they're a single or a twin lamb. Twin lambs, of course, are lighter than single lambs. Other than that, the distributions are about the same. The feeding regimes, potentially some difference with the HM feed, so given weight gain early during pregnancy and then maintenance for the last half seem to be maybe a little bit lower. The others all about the same maybe. But less evidence for this than the others, and maybe something in shearing. So if the ewes were shorn, then their corresponding lambs were a little bit heavier, but lots of overlap, not much evidence. So let's write something about that. So clear evidence for difference in birth weight between singles and twins. Twins lighter, and difference between male and female lambs. Males heavier. Less evidence, but still some for feed making a difference, with the HM feed treatment seeming a little lower on average than the others. Shearing the ewes possibly increased lamb weight a little bit. Okay, next we're going to look at a linear model just using feed. Okay, so we're modelling the birth weight in terms of the feed. And because the feed is of course a categorical variable with more than 2 levels, we're going to use the analysis of variance table with the Anova function to assess that, right? Because if you just look at the summary table, we're going to have a multiple p-values associated with feed, right? You're going to get one for HM, one for MH, and one for MM. Of course, HH is the baseline group here. So, it's hard to interpret all of these p-values all at the same time because, one's shows some significance while the other ones don't, right? So it's like, well, what's the conclusion here? It's a little bit hard to see. That's why we look at the Anova table, because it just has a single row for feed, assessing whether feed is important, and you can see that it is not. So what we see in our data might arise by chance about 11% of the time if in the population there was no difference between the feeds. Okay, so some notes about this. So from the Anova table, we can see a little evidence that feed makes a difference, as the p-value is fairly large at 0.11, i.e. We'd expect to see the differences observed in our data by chance about 11% of the time, even if there was no effect at all of feed in the population. Maybe we'll make it our sample, i.e. our sample data are consistent with no difference due to feed treatment in lamb birth weights. Okay, remember, this doesn't mean that feed doesn't make a difference. It just means if you look at feed alone, it doesn't help explain the differences in lamb birth weight. Right, again, you can see that the multiple R squared here is low, right? 3%. Only explains 3% of variation in birth weight. So next we're going to fit a more useful model that takes into account the other things that we know make a difference, right? So if you look at the feed plot, right, then part of the reason we can't see this difference in centre when we just look at feed is because all of these, there's so much variation within each feed treatment, right? But we can explain that because all of these ones that are light, all of these ones, these lambs in the sort of 3 kilo range, they're all twins. And all of the lambs in the 7 kilo range, they're all singles, right? So once we include rank, which is making a big difference in the weight, we're going to explain some of the variation within the feed. And so we may be able to then spot the variation between the feeds. Okay, so let's have a look at this next model with everything in it. Okay, and what we see here is that when we look at the Anova table, we see that sex is important, rank is important, feed is important, and sharing is important. Okay, everything is important. Okay. So from the Anova table, remember, always look at this first, particularly when you have categorical variables. We see that everything is important as the p-values are all fairly small. So we know that feed, sex, rank, and sharing are all important variables that affect the average birth weight of a lamb. Okay, how do they affect the birth weight? So we know they affect the birth weight by using the p-values in the Anova table, but how? We can look at the summary table. Right, so what we can see from the summary table is that the males are heavier compared to the females, which will be in the baseline group, right? The one not listed here is in the baseline group by about 385 grams. So males are heavier on average, all else being equal, by 385 grams. We see that twins are lighter than singles, right, the baseline group, by around 1 kilo, right, 1.1 kilos. Shearing makes a difference. Ewes that were shorn had heavier lambs by about 240 grams, right, from here. And we can also see these differences in the feed treatments, right? The HM feed treatment does worse than the others, about 450 grams lower than the HH treatment, with the M and HH treatments being similar to each other, and the MH treatment being in between. Right, so what I'm using for that is these numbers here, right? So the HH treatment is in the baseline, it's the one that I don't see there. The HM treatment is then 450 grams below that baseline, so the HM treatment is 450 grams below HH. MH is 240 grams below HH, so it's in between the HM and the MH, and the HH. And the MM is then almost the same, right? So it's a little bit, only a tiny little bit, 20 grams below the HH group. So essentially HH and MM are the same, MH is a little bit lower, and HH is lower again. Okay, so this intercept term here represents the baseline of all groups. So it's going to be a female lamb, a female single lamb, born to a ewe that was on the HH feed treatment group who wasn't shorn. Okay, so let's write that down. This model explains how much? 33% of the variation in body weight and lamb birth weight. So that's not a huge lot, right? So we've got so around a third is what it explains. There's 2/3 left over, right? And that kind of makes sense, right? Because all we have here is grouping variables. So the only thing we can distinguish is the difference between the group means. We can't explain any of the variation within group. Okay, and so this is something that typically happens when you've basically only got grouping variables, is you don't tend to explain all that much of the total variation because there's a lot of variation left over within each group. Okay, so nonetheless the model is going to be really good for predicting the average, but it's not going to be that good for predicting individuals. So good for averages, but not very good for predicting individual lamb weights. Okay, and lastly, we'll visualize the model. We should get the same overall conclusion as we got from the summary. So you can see here, there's a difference between male and females, with males being bigger. Clear difference between in the rank of the lamb. Twin lambs are smaller. HM group is the lowest, and HH and MM are about the same, and then MH is in between, and shearing makes a difference, a small difference to overall weight. Okay, so same conclusion from the summary table, just a bit easier to immediately see how different groups are placed. E.g., really easy to summarize the feed variable, which from the summary table was trickier. Right, so the main advantage of VisReg is it allows you to see, once you know there's a difference from the Anova table, p-values, you can then use the VisReg in order to figure out where the differences lie. So you can easily then visualize, what's the biggest group, what's the smallest group, which is a little bit easier than determining it from the summary table. Okay, in this case, it's not too bad from the summary table because we can the direction of all of the groups compared to the baseline is the same. So we know that the baseline group is the highest, and we can sort of use the magnitude of the estimates of each difference in order to figure out that the MM group is about the same, the HM group is the lowest, and the MH group is in between. But of course, it's much quicker to see that from the VisReg. Okay, so my advice to you is use VisReg whenever the summary table is not particularly obvious to you. Okay, and lastly, we might want to check the model assumptions. So we're going to plot our model, which is LM2. We'll turn the smoother off, and we'll have a look at the 4 plots. So these look fine to me. So often, so we don't have to worry about this kind of vertical striping effect that we have here, right? Where everything is kind of, has gaps in the x-axis. This is in fact what we'd expect because on the x-axis is our fitted value, right? So that's the estimated average birth weight. And the only thing we have here are grouping variables. So all we have is all of the different possible groups. So essentially we've got 4 groups for rank, 2 for sex, 4 for feed, 2 for sex, 2 for rank, and 2 for sharing. So all up we've got 2 times 2 times 2 times 4, which is 32 different groups. And so we've only got 32 possible fitted values, which is why you get these vertical stripes. We've got multiple lambs within those categories, right? So that's what the stripes are. We don't care about that. All we care about is there a trend in sort of the Y? And there's not, right? Everything's kind of flat. So linearity holds, equal variation holds. The variation is about the same as 0 across. So we can write about that. So linearity seems okay, as does equal variance. As there is no curving trend on the residuals versus fitted plot, and all the scatter seems even as we move from left to right. Normality seems okay, little bit of difference at the end here, but no big issue. We ignore that one, and the residuals versus leverage plot again seems fine because all of the points are within the Cook's distance bands. We can't even see them. Okay, so no points of high influence, as all points are well inside the Cook's distance bands on the residuals versus leverage plot. We can't even see the Cook's distance bands. One thing that is a problem here, though, is independence. Now, remember, we can't assess independence from these plots. Okay, the only way to assess independence is to know how the data were collected. And why I say independence doesn't hold here is because we have twins. Right, we've got twin lambs, right? If we have a look in the data set, we can see that lambs 10 and 11 here, these first twin lambs were born to the same dam, the same ewe. So lamb ID with ID 133 and 134, they were twin lambs, both males, born to the same ewe. So we'd expect that lamb 133 and lamb 134 will be more related to each other, as they're twins, than they would be to other lambs because they are twins, right? And so there's going to be a lack of independence for any of the twins, right? So these ones here, row 12 and 13, lambs 142 and 143, again, they're going to be more related to each other than they would be to this twin pair, right? Because they were, they shared a uterus, right? So let's write a little bit about that. We have twin lambs here, which are likely to be more related to each other than to other lambs. So independence will likely not hold. One way to potentially fix this problem is to pick just one of the two twins at random to include in the data set, right? And redo the analysis. Okay, so that's one thing that we could try and do to fix it. So we'd go through and would remove at random one of the two twins, so that we only had a single lamb for each U, and then we'd redo the analysis based on that. The disadvantage of that is, of course, you're losing information because you're discarding observations in the data. But at least you're fixing the independence problem. So it could be used as a, if you like, a sensitivity analysis just to check that your results hold when you fix up the independence assumption. Okay. I won't do that now, but you're welcome to do it if you wish. An easy way to do it is just to load up that data into Excel or something and just remove one of the rows, and then save the data, reload it in, and away you go. Obviously, there's ways to do that in RStudio as well, but that's kind of the quick way to do it here. Maybe because I've got time, we'll just have a quick look, shall we? Why not? Lambs, one only. So we're going to take our lambs data set, and so I'm going to load some libraries that I know how to. I'm going to load the tidyverse, which is basically for a library for transforming data. We're going to group by DAM ID, and we're going to summarize. What are we going to do? Right, so I'm just taking the first one. The first lamb from each pair. So you can see if I have a look at lambs one only, then you'll see that I've only got a single one from DAM ID 102/95. Right, so it's a twin, but I've only got the one. I don't have the other. Okay. And of course, I've got less entries, only 134, whereas for lambs, I had 204. So I've thrown away 70 observations. So I'm going to be losing power. But then let's refit the model with this and see what happens. So we're going to go LM3. Let's just copy and paste it so I don't have to type it all back in. Grab that block there. So we're going to have a new model, LM3, then do the ANOVA and summary of it. And we're going to use lambs one only instead of lambs. Okay. So when we do this, what happens? So we find now, so this is interesting, we find that feed is only marginally important and that sharing is no longer important. Okay. So that's interesting. So when we rerun this model on the reduced data to try and fix the independence problem, we find that sharing and feed are no longer important. We notice though that the direction, the effect is the same, right? So that the sharing still increased the birth weight, but the uncertainty associated with was higher, right? So there's a trade-off here between trying to get the model assumptions right and losing observations, and thus losing statistical power. We've thrown away 70 observations in order to try and fix the independence problem. So our data set is quite a bit smaller. So standard errors, uncertainty will be higher. So there's other ways that we could fix this as well, which allow you to keep those 70 observations in, but still correct for the potential of the lack of independence. And using those methods, they're called random effects models or mixed models, with essentially an effect for the dam. Using those sort of models, what we'll find is that feed will still be important, and so will sharing, but marginally so. So there's some evidence here that sharing makes a difference, and some evidence here that feeding makes a difference, but it's really, we're kind of on the borderline. We'd really want a bigger study to really show the difference here. And if we had a bigger study, then we could just choose one of the lambs from each twin pair, right? So if we, perhaps have 1,000 lambs, if we use maybe 200 or 300 dams, then even if we reduce just to a single, just pick one of the twins, we'll still end up with 200 to 300 observations in the data, and we might then have enough power to be able to distinguish the relatively small effect of sharing.